Hi everyone. I'm still quite far away from Europe at the very moment. Quite the opposite side of the world, still Australia. So I'm doing this remotely. This is a presentation on the paper I've written called Parallel Garbage Collection for Steel Bank Common Lisp. So as the name might suggest, I have implemented a new garbage collector for SBCL. This collector can use multiple cores, and it can sometimes run faster by not copying the objects regardless of parallelism. It uses new approaches to doing conservative root finding and non-moving generational garbage collection, which I'll get into in a bit. It's not upstream yet. Part of the reason why is, bemusingly, it should still move objects sometimes. Not all the time, but it needs to move them sometimes. But when we're not moving objects, it should be quite easy to make mostly concurrent, because we don't have to handle moving the objects concurrently and particularly frequently. So currently, SBCL uses what's called a generational copying, well, it's copying, but the name of it is Generational Conservative Garbage Collector, or the GenCGC. It reclaims most of the memory by copying the live objects, which leaves rather large spans of free space. The simplest copying collector simply has two spaces. It copies all the live objects from one space to the other space. Each of these is called a semi-space because each one is half the size of the heap. This application can allocate the objects after we do a collection as such. We're able to just increment a pointer from the end of the last object that we copied to be able to allocate more objects, which is called bump allocation. Now, this is very much an oversimplification, very much one. SBCL, for example, doesn't use two contiguous spaces. It actually partitions the memory into ranges called pages. Each page is how did I write that? Each page is assigned a semi-space and other things like generation, types, and other such metadata using a page table. So the application can still bump allocate into each page, but once it exhausts a page, as it's just about to do here, if we're able to get one more object in this new page, it will have to find another page that we can allocate into, which will probably be this free page here on the right. There are some strengths and some weaknesses to this approach. One strength is that by copying all the objects, we quite easily avoid the fragmentation, where the free space of the heap is actually split up into various small ranges that we can't use too easily. But in reality, applications don't tend to fragment that much. They tend to allocate objects of the same sizes, and the objects tend to be freeable in large clumps. So in practice, you get rather large spaces that are quite easy to allocate into. Thus, it's mostly wasted effort. And also, the copying wastes space because we have to reserve space to copy into, even if it's not an entire semi-space. Another nice thing about copying, as compared to some schemes, is that we can use the bump allocation, which is very simple and very fast. But, as I'll get to later, we can bump allocate with algorithms that aren't copying. One weakness, which is more inherent though, however, is that copying requires performing more memory accesses than other algorithms which don't move objects. When we do the copy, we have to read the object from memory and then write it back to memory somewhere else, which requires more memory traffic, and it also pollutes the cache memory as well, which isn't particularly great. If we want to parallelize the copying algorithm, we have to have very careful synchronization to just copy every object once. And this also is subject to our higher use of memory bandwidth, which will make scalability more difficult. But all these weaknesses might not be so bad if there are only a few live objects, which are common in a generational collector, which we'll get to later. In such a situation, the copying does less work, even though it seems to have more difficult work, than algorithms which scan the whole heap, which is the one I'm about to explain, does do a bit of that. When we have a slow-ish garbage collector, there are a few workarounds we can look at. We could increase the size of the heap to make the garbage collector run less frequently because we have more space to allocate into, which will improve the throughput because we're not running the garbage collector so much. However, this doesn't scale particularly well when we're parallelizing a program. Suppose we have a program which uses tasks. Each task can be run in parallel. We have n tasks, then we're going to allocate n times as fast, and each garbage collection is going to have to scan n times as many live objects. So if we want to keep the garbage collection overhead constant, we actually need to grow the heap by n squared, which is going to grow rather quickly. If we increase the size of the heap, we also can run into issues with locality and reference and not making good use of the cache memory, which also isn't great. For latency-sensitive applications, increasing the size of the heap to reduce the number of times we do garbage collections makes the time between pauses longer, but doesn't actually shorten the pauses. It might actually make them slightly longer, in my experience. We can also avoid trying to generate garbage. For example, in Common Lisp, we have the dynamic extent declaration, which can stack allocate object, and we can also try and mutate objects more, use in-place algorithms, but I think that these hinder the modularity and simplicity of programs, so I prefer not to necessarily rely on these. So the algorithm I've implemented is a mark region garbage collector, similar to the Imix collector. Now, this collector is able to reclaim memory without moving the objects, but it still allows the application to bump allocate to get that speed. After partitioning the heap into pages, we then partition the pages into lines, each line being 128 bytes, and the collector is able to reclaim lines individually. The application can bump allocate into these runs of free lines, and the collector traces through every live object when it's going to reclaim and perform garbage collection, and then it can reclaim any lines unused in this live objects. In this diagram here, the allocation range has just allocated objects into this line here. These two lines already were used by these two objects here, and this this line on the right, is not used by any objects. And note that this third one from the left is still used because the green object here still overlaps it, so the line is still used, even though it doesn't start in that line. So when I speak of tracing, I'm speaking of an algorithm which recursively visits all the objects that the application could possibly access. Now, to make our descriptions more succinct, we speak as if we're coloring in the objects. We start by having all the objects that we haven't visited be white, and then when we visit the objects, we turn them grey, and then once we visit all the objects reachable from slots in objects, we turn that object black. A semi-space collector is able to represent the grey and the black objects using contiguous ranges of the two space that we're copying into. This is called Cheney's algorithm. When we introduce pages, it's a bit trickier, but the basic idea of partitioning the pages and ranges like this still remains. But we don't have a copy and collect this, so we need a different way of representing the grey set. I need to put my phone on mute. That was it's an email, and I'm going to bet you that's the SBCL mailing list just to mess with me. The basic idea still remains. The set needs to be represented in a different way, a set of grey objects. So to do this, we use a list of packets, which are little arrays of pointers to grey objects, following a garbage collector designed by Oshia et al. At most, in practice, I found that this list used just about 3.7 megabytes of memory in testing, which is quite small compared to a semi-space or the number of pages that we need to reserve, for example. We can parallelize this because we have packets. We can give each thread a packet of objects to process, and then have it write out its own packets. And this also reduces the need to synchronize because we only have to grab a lock when we are actually acquiring packets to read and write into. Because we have all the pointers in our arrays, we can also prefetch ahead. We can use prefetch instructions to tell the processor to load pointers ahead of time, which covers up particular latency of using the primary memory. Now, one of the first techniques that I've come up with here is that of the conservative root finding. I'll start by first defining the roots. The roots are the objects immediately accessible by the application, such as in the lexical and special variables held by Common Lisp programs, and some other global data structures you don't get to see, such as tables of packages and classes and some such. One complication is that the SBCL compiler can use boxed tags, which have type tag pointers on the end of the pointers, so we can tell types of those, and it also has unboxed values without tags. On a 64-bit system, these are the 64-bit integers and double floats. These don't have type tags on them, but if we're really unlucky, they can look like pointers, and we have to manage these very carefully. So the collector has to correctly handle the unboxed values despite not knowing which are boxed and unboxed. So when we have something that looks a bit like a pointer, there are a couple of ways that we can figure out if it is actually a pointer, which object it's actually referencing. When we have a copy and collector and everything is bump allocated and contiguous, we can simply step over each object to find the pointer. But we can't do this for our collector because our objects are not contiguous. A non-copying collector, in such a situation, can consult a bitmap where each bit tells where an object starts. But it takes time to write into this bitmap, and it's particularly annoying when we're not on the x86 instruction set, because x86 has a instruction which lets us write into a bitmap with the one instruction, whereas we have to do the computation to index the bitmap ourselves on other platforms. However, both of these are somewhat overestimates here. When we're dealing with our collector, because we still bump allocate, all the objects we just did allocate are contiguous. And also, we don't actually have to record all the objects, just the ones that the collector might end up finding. So, I use kind of a hybrid approach. I call it a lazy object map, where, for the most part, all objects that have survived the collection already have the bitmap set. But all objects that we just allocated are all the objects that we just allocated are have lines which are marked as fresh, and they don't actually have any bitmarks set. And so when the collector finds one of these, it finds the enclosing fresh range, and then computes the bitmap for that, as it might do here. Now, we don't actually have to compute very much of this bitmap at all. First off, we have the weak generational hypothesis that most objects die young. This seems to be the case for common Lisp programs. And most objects aren't referenced from the registers and stack locations that we have to handle conservatively, so we don't have to set very many bits. At most, I found that we only had to do about 600 kilobytes of heap objects in testing, which is quite small. The other approach that I've invented here is one of the non-moving generational garbage collection. The issue here is that we have a generational garbage collector. It focuses on trying to collect new objects because the new objects tend to die sooner than old objects. This requires two things of the collector. We have to be able to partition the objects by generation, and we need to be able to remember pointers from old objects to new objects so that we can collect the new objects correctly. Now, the copying collector first assigns each page a generation in order to partition the heap. This is acceptable because the collector can copy between pages while it's promoting from the new to the old. To remember pointers, we still use the card marking skip, which involves marking that a range of memory called the card was dirtied when we write a pointer in that card. And then when the garbage collector runs, it scavenges each of the cards, looks for any old objects on dirtied cards, and checks if there's any old to new pointers on those. So if we were to assign each page generation like the copying collector, we couldn't actually reuse any memory in an old page until there's no objects on it. So here is a page here, it is new, we've allocated some objects on it. When we do a collection, most of the objects go away. We can then keep allocating onto it, but then disaster strikes when we try to promote it to old. We cannot use any of the space anymore because we cannot put new objects on an old page. The opposite approach is to assign each object its own generation. But there is an issue here that first, we don't really have any space to put the generation. If we have a const cell, that's just 2 pointers. We don't have any extra space. We could use a side table, but the side table would be quite large. Another thing is that when it comes to updating on the card, we can have multiple generations on the one card, and the collector can become confused as to which were updated. Suppose here I have this new object, which I'll update. The whole card is dirtied, and the collector will scan the old object, even though it doesn't actually need to. So we can get around both these problems by making the lines the same size as cards. We don't lose precision in reclaiming memory because we can't reclaim parts of lines, so we don't lose any space doing this. We also don't lose any precisions in tracking updates. For the same reason that we can't reclaim parts of lines, we can't have different generations on the same line, so that is also not a problem. Having these be the same size also makes it quite easy to locate the dirty and the old cards. We can specifically use the single instruction multiple data instructions to locate these really quickly. And because we're only storing one generation per each line, we have a very small space overhead of just 1 over the 128. So I then benchmarked this garbage collector to see if I was actually doing the right thing here. I had to choose perhaps quite odd benchmarks here. The CL benchmark suite, which you might be familiar with, I don't think it generates much work for the garbage collector. The only exception to this is that the BOEM GC can be scaled up quite easily. We can have a K parameter, we can make it quite large. I'll get to that later. One might think that we can scale down the heap in order to make the garbage collector run more, but I don't think that's reflective of many applications because the cache memory would become too effective because the cache memory is relatively large. So I don't think we should be doing that. I had to pick my own benchmarks then. I picked 2 micro benchmarks and 2 macro benchmarks, which I'll get into. These are all run on a virtual machine with 12 cores. So the first from CL Bench is the BOEM GC benchmark, which creates a large number of binary trees in various stages. The garbage collector has to trace all of these. Poor garbage collector. It produces no fragmentation at all. All the trees in one stage get allocated, and then at the end of the stage they're all reclaimable. So we don't get any gaps in the heap. In this benchmark, the marker region collector performs quite well, quite competitively, even on just the one thread. The mutator time is slightly slower here. That's the time the application takes, rather than the garbage collector. There are second-order effects here. But otherwise, the marker region collector performs quite well, and we can see that the garbage collection time also decreases with multiple threads. Another micro benchmark here, is the ring buffer, which is a rather unfortunate benchmark for generational copying collectors because it has a ring buffer with message arrays. Each array is just an unboxed array of bytes with 1 kilobyte of bytes in them. And a copying collector has to just keep copying these. It can't do much better than that. And the objects, the messages, all survive around the same length, and that's quite long. So it's very unfortunate for a copying collector, as we can see here. With the blue line as the copying collector, it performs quite poorly compared to the mark region collector. This is also a problem for a similar designed copying collector for the Glasgow Haskell compiler, which is where I got the benchmark from. Now, onto the macro benchmarks. Cambria is a commercial video game, which you've already heard about today. If you haven't played it, play it. I'm not going to get further into that. I heard reports that there was some stuttering on the older hardware, which might have been caused by JC. We might not be able to reproduce just yet. It produces very few objects which survive garbage collection, which, as I had mentioned in the strengths and weaknesses, is great for a copying collector, but not great for the smart region collector. I needed to run this on my desktop because I need graphical output. I couldn't get capturing to work. I couldn't get to replay the inputs I wanted to play, so I had to play this manually. In order to try and simulate slower hardware, I just made the frame time limits shorter. So we have a 16 milliseconds, about 60 frames a second, and I just kept trying and seeing how many frames would fit in 12 milliseconds, 8 milliseconds, 6 milliseconds. As we can see here, the copying collector still outperforms mark region, even with, say, 4 threads. In this case, the mark region collector did suffer from fragmentation. It took a lot of time to scavenge and a lot of time to sweep, relatively speaking. 160 megabytes of the objects in the old generation were spread across over 660 megabytes of pages at one point, which is quite a lot of lines that it has to look for in order to check if there's any dirty and old cards, as we had mentioned. The other macro benchmark I have is one I wrote called Rebrand. It's a fuzz tester for a compiler I wrote. It tries to find cases where the compiler fails to actually compile anything at all, and when the compiler generates bogus code which reads out of bounds or produces out of bounds results. There are different workloads using the interpreter and the compiler. The compiler of SBCL generates longer-lived objects and more GC work. I did a bunch of stuff to make it more reproducible for a benchmark as well. For the interpreted version, we see that the marker region collector with one thread is slightly slower, but parallelization does help here. On this hardware, I did find that the application itself seemed to run a bit faster with the non-moving collector, so the memory layout seems to be a bit better here. But it was closer on my desktop. I didn't get many samples runs of that though, so I'm not too sure. But I think that there's a bit of a hardware-specific thing there. With a compiled version, however, there is a much greater difference. The parallelization really helps here because, as you can see by this axis here, we're really waiting for the garbage collector here. Parallelization really helps here, and we get another similar curve here, except that the marker region one here is more steeper. This is because that when we have a larger heap, we spread out the surviving objects over more pages, which means that we have pages with less or fewer objects on average, which means that the mutator doesn't have to grab so many pages and doesn't have to take a lock so often, which helps with scalability and makes it run faster. So, there are a few things that we still need to do before I can really upstream this or do anything with it, really. We still need to compact the heaping frequently. Even though it doesn't have to be every time like a copying collector, we obviously have problems with our fragmentation. So I've started to implement an incremental compaction algorithm, which moves just the fragmented pages in one collection, and doesn't have to compact every collection either. The SBCL also uses a separate another space for another heap called the immobile space, which can use to store some objects using 32-bit pointers, which we also have to support at one point. This is used for object headers to store the pointers to layouts of objects, and also for having constants in compiled code. This reduces the space overhead for both of these. As mentioned before, we can also follow the OCI et al. Garbage collection algorithm in order to make the tracing concurrent, which would also help with pause times. Things that I don't really expect to implement in this collector soon, but I'd really like to investigate, include checking out the number of generations SBCL uses. It uses 6 of them, but most collectors nowadays, say for example the one in the OpenJDK just uses 2 of them, which is quite a few smaller. If we had fewer of these, we could make compaction a lot easier because we'd have fewer generations that we'd have fewer older generations that we wouldn't be able to compact while looking at a younger generation. For the old generation, it might also be worthwhile to use particular reference counting algorithms, which face fewer updates. The updates can be done in an embarrassingly parallel way when tracing requires a single graph traversal, which is not embarrassingly parallel. And also, it does work proportional to the number of updates to the heap, which we hope is small, and not the number of objects, which could be larger. With more multi-core systems, with particular caches, chiplets, and relatively slow main memory, I think we also should revisit thread-local garbage collection schemes where each thread has its own private heap that it can collect by itself. This would help with scalability, since we have an easy way to partition the heap between threads, and it would also avoid global stop-the-world pauses if most objects can be reclaimed in private heaps. So, some credit where it's due, because, well, I did make the garbage collector, but I would be very stuck if I didn't have all these people to help me with it. There's quite a few people with me. Let's bear with me here. Statsberger and Doug Katzman helped me get up to speed with how the garbage collector interacts with the rest of Steelbank's common Lisp. Steve Blackman and Kunal Soreen had discussed IMIX with me to come up with these ideas in this presentation. Nicholas Hafner helped me with getting the auto-vectorization to work in the C compiler and also guided me around the Cambria source code to do this investigation. Paul Kwong and Larry Massenter had contributed to the design of the internal memory manager used by the garbage collector to manage packets. CliffClick helped me make sense of the benchmarking results. Grindwork Corporation provided me with access to a virtual machine for the benchmarking. Jan Moringian, Kunal Serene, Elijah Stone, and Robert Strand had provided comments on early versions of the paper. Right, I think that's everyone. Oops, not everyone. There's probably a few other people I can think of. Yes, I'll do that. Thank you. Thank you very much. You can get the collector from this first link here, and you can get this slide deck from this link here. Thanks. Let's unmute this.
Thank you, Hayley. Any questions? Yeah. Okay. Be there.
Yeah, I'm just wondering, in the status quo with the non-parallel SBCL garbage collector, if you have a multi-threaded application with a lot of this threads running, what actually happens? Does the whole world stop while just one CPU core is doing all the collection? So is this more of a throughput or a latency optimization? If you get what I mean.
Okay, so the question was whether if you have a multi-threaded application, whether the whole world stops when you do a collection in SBCL.
Whether the whole world stops when you do a collection in
Yes, at the present moment, yes. If you have all the threads, they will stop waiting for the garbage collector to complete. That's a stop the world pause, yes.
Waiting for the garbage collector to complete. That's a stop the world pause, yes.
Could you maybe repeat that?
It is stop the world.
It's stop the world. Okay,
Yeah.
thanks. Okay, next question.
Yeah, I just have a quick question. I think at the end of your presentation, for further work, you described quickly how you could maybe use reference counting to speed things up a bit, but only for old generations. And because I don't know much about this topic, I was wondering how you can just do reference counting only for old generations when what I understand is that there needs to be instrumentation in the code, and it doesn't seem like you could instrument that only for running for old generations because the code is compiled ahead of time. So I just want to know what exactly you meant by reference counting for only old generations and how that would work.
Yeah, so there's a question about how you would do reference counting for older generations and like how that would work without the need for instrumentation.
Sure. So to implement reference counting, there was a paper I'd recommend, the ulterior reference counting. For the current generational collector, the compiler has to insert code for the card marking. We'd use a slightly different write barrier in order to allow for reference counting of the old generation, whereas the young generation would skip the write barrier. Basically, I would just recommend reading that paper.
More questions? No, one more?
I was wondering about previous work already made in research about concurrent garbage collectors. For instance, if we have looked at the Java or the .NET, how it compares, or if it would be possible to implement in SBCL something that would split the work over multiple threads, stop some threads and not others, I don't know, split the heap, avoid global collections until as much as possible, for instance.
Okay, if I understood correctly, the question is like how your work would compare to prior art in parallel collection in .NET and similar, and whether it would be possible to parallelize the work or split the heap or do that kind of stuff to try to stop the world?
Sure. So the Osia et al. That I reference was a garbage collector, I think, used by IBM for Java. So I am basing it off prior work in a JVM, to be fair. It is quite a bit earlier than the contemporary, say, JVM algorithms I'm much familiar with, say the G1, ZGC, for example. It is quite a bit earlier than that. As to partitioning the heap, well, we do strictly speaking do partition the heap already between the older generations and the newer generations, which does reduce the stop the world pause when we do the new collections. But I suspect I think you're suggesting some other kind of partitioning the heap approach to partitioning the heap rather.
No questions? Then question from me. So this is for SBCL. Is this now accepted in SBCL or is it going to be part?
So, question: is this going to be accepted in SBCL, or is this already in SBCL?
It's not upstream to SBCL. As mentioned, I still want to get the compaction and the immobile space working at least before getting it upstreamed, I think.
Okay. No more questions? Thank you, Hayley.